for this week. Okay, so let me remind you that what I wanted to do. So X over C, dimension D, smooth, projective, manifold, F, rational map, dominant. And then I have to choose a polarization, so an upper line bundle, L. And so I define degree K of F as per pullback, this wedge K minus K. And so I have to, I'm going to make this a little bit more precise. And so I want to define out of this lambda K of F. So justify the fact that the limit exists. Degree of Fn to power 1 over n. And so essentially prove that this sequence of degrees that depends on L a priori are submultiplicative up to uniform bounded constants such that this exists. And then state a couple of things, general facts on these numbers. Okay, so I need, so here you see that there is a dot. So I need some basic facts on intersection theory. So don't worry, I'm not going to summarize Fulton's book in 5 minutes. So the good point is that we are intersecting basically, forget about F star, but we're intersecting basically Chern classes of line bundles. So we are only intersecting line bundles. So this is much, much, much simpler than intersecting general cycles. So let me start. Let's say. So basically, what I want to do, so I have exactly that in dimension 2, the space of all divisors. Sum of AI, Zi, so codimension of Zi is 1, AI is an integer. And then I want to define also the narrow Savary space, which is the space of divisors X modulo numerical equivalence. Okay, so so how is this defined? Well, you say that two divisors. Well, okay, so I have to tell you it's the same definition as in dimension 2, except that now I have to tell you how you cup a divisor with a curve. And how to do that is just like in dimension 2, a divisor defines a line bundle, let's say OXC, so you can restrict it to C, and you look at the degree of this line bundle of C. Okay? And again, Z1 is numerically equivalent to Z2, the same as the intersection on any curve, or the same for any C curve. And so the first fact, I think, yeah, okay. And also what I want to, let me follow my notes, because last time I didn't do that, and it turns out to be delicate. So also, I want to be able to intersect D divisors. So this is going to be a number. Okay, and okay, so here I'm going to cheat a little bit, but one way to do that is, okay, it's going to be multilinear, or linear in each variable. So you only need to define this, let's say, for irreducible hypersurface. And so the way you can interpret this number is like this. Then you look at the fundamental class of this guy. So a priori, this is in H2D minus 2 in the homology, 2D minus 2 X comma Z. Then you take the Poincaré dual of this guy. Go back to H2 Durham. And then you kept this in Durham cohomology. So this is in H2D Durham. Okay, coefficient in Z does not make sense, let's say. And in fact, these things is canonically by integration, canonically isomorphic to R. So when you do this with the cohomology, a Durham cohomology, you get a real number. But then, in fact, these cycles are defined integral cohomology, and so you can check that the numbers are equal to or integers. Okay, and you can also play around by writing divisors at difference of ample divisor and get back to the definition like this if you want. Okay. So now I would like to, so the one fact. Yeah. Hello, baby. Yeah. So what we're going to do is to, as in dimension 2, look at the pullback of F or morphism from the neural survey space of X to itself or to some other varieties. Okay, I need to pull back, to push forward, and so on. And so here, the first thing is this, the neural survey space of X can be quite tricky, right? It's, I don't assume that X is rational. It's just any projective variety. So the first observation is that this space, let me tensor it by R so that I kill any possible torsion. So these things is finite dimensional. Sorry? Because I'm killing by this. Okay, yeah, sure, okay, yeah. Anyway, it's finite. The main thing is finite dimensional. Yeah. So how do you see this? Just one word about this. So this is true over any field. So if you want to check this over any field, you have to use Étale cohomology. I'm not completely sure that I know what this is. But at least over the complex numbers, then you have this map that I use to define the intersection numbers from the set of divisor to the Durham cohomology of degree 2. And then you have this map, neural survey space. Okay, so this is this map here is far from being, let me tensor everyone by R. You have R here, okay. So this map is not surjective, far from being surjective, but its image here is a subspace inside the Durham cohomology, which is finite dimensional. And since I define this intersection, this numerical equivalent with things like this, then in fact you get a map which is surjective. And so you get finite dimensionality because this guy is finite dimensional. Okay. Okay, so I need a little bit more about this finite dimensional space. I need positivity properties. So I managed to avoid, for 4 hours, I managed to talk about dynamical degrees without pronouncing the word nef. So it's problematic. But so we need, let's say, positivity properties. In the null survey space. Okay, so there are two basic notions of positivity properties. So you say that, let's say, alpha, it's a class. So suppose first that alpha wait, okay. Yeah, sorry. The way I want to say is like this. Okay, so suppose Z is a divisor. Then Z is said to be effective. And we write Z greater or equal to 0. If and only if Z can be written as sum of AI Zi with AI non-negative. Okay? And then we can look at the set, so you can look at the set of all effective divisors, and you look at all the images in the non-server space. Okay, so this is a set of integral points, and what you can do is to look at the convex hull of this set of points and take the closure. So this is called the pseudo-effective cone. So this is a closure of the convex hull of all classes Z, the inside the set of divisor of X, and Z effective. So in other words, if you pick an element which is pseudo-effective, it's a real class, so it's inside this finite dimensional vector space, and it's a limit of Zn, maybe times alpha times Qn, Qn rational, and such that the Zn are in div of X and and effective. And there is also another, so this form a cone, and there is a smaller cone which is even more important than this one, which is called the Neff cone. So this time it's a subcone of a convex cone of the set of the cone of pseudo-effective classes. And this time this is the closure of the convex hull of ample classes. So if you want of classes of Z such that Z is ample. Okay, so again, this is the same thing. So it means that any class alpha and F can be written as the limit of Qn rational, maybe here Q plus positive, times some ample line bundles. Okay, so I need a couple of facts about these cones that I will not spend too much time on proving them. So the Neff cone, so any ample divisor is effective. So the Neff cone sits inside the pseudo-effective cone. And just by definition, they are closed convex cone. But also, this cone do not contain any line. So one says that they are strict or salient, which means that there exists a hyperplane. So let's say this is the biggest one, Psef. So there exists a hyperplane that touches the Psef cone only at the point 0. Okay? So in other words, plus if you have a class such that alpha and minus alpha belong to the pseudo-effective cone, no other option, alpha is 0. Okay, so the Neff cone is characterized by the following nice condition. So I said it's a limit of ample. So if you have an ample divisor, when you restrict to an ample divisor to any subvariety, it's still ample. So in particular to a curve, its degree is positive. And so when you take limits of this, it means that the intersection number of alpha with any curve has to be non-negative. So the claim is that it's a characterization. So for any curve, alpha.c is non-negative. What do I need? So I need a little bit more. I need that the interior of these two cones is non-empty. In fact, if you look at the interior of the Neff cone, this is an ample cone. So this is ample cone here is the cone generated. You don't take the closure, generated by ample classes. So the problem is that I'm not saying that these are all ample divisors, but the divisors are integral, right? And here I'm in NSR. Okay, and last thing, if you take Z, pseudo-effective thing, and you take Z1, ZD minus 1, Neff, so it's going to be something that follows from this. If you intersect Z with Z1, Z2, ZD, then this is non-negative. Okay, so how do you see this? So if you believe in this characterization here, being an F means that you can approximate up to multiplying by some positive rational number. You can approximate Z1, ZD minus 1 by ample divisors. And so then you can take general sections. And the general section of ample divisors, or maybe you take a multiplier of them so that the divisors are very ample. Then they are determined by the effective curve. So here it's going to be, so by approximation, this is determined by an effective curve. And so by this, what I'm saying here, blah. Wait. Qu'est-ce que je raconte? N'importe quoi. Yeah, okay, well, it's still true, but it's not what I'm saying. Whoops. Okay, so yeah. It's a dual of this. Okay, sorry. Yeah. There are going to be many more mistakes, I'm sure. Okay, so this is not from this. So here you see this because you may assume. You may assume by continuity that all these guys are ample. And so by taking a general section, then this is represented by a curve that do not sit inside C. Okay, that intersect Z inside Z. Sorry. Okay. What? Okay, so out of this, so this is Kleiman criterion. I'm not going to explain this also. One way to see this, for instance, since I use current and so on, one way to see this is that, in fact, so this is very well explained in the famous set of notes by Demailly. And so one way to see this is that, in fact, if you have alpha a pseudo-effective class, it's a limit. It's not determined by an effective divisor, right? But still, you can show that this is determined by a limit of these divisors, and which is a so-called positive closed 1-1 current. And now, in fact, you can look at the mass. So you take your favorite Kähler class, omega. You can look at the mass of these things. This is the integral of this. And this has to be non-negative. But then you play around by minus alpha also psef. It means that the opposite is also non-negative. So it implies that the mass of T is 0, which implies T is equal to 0. Okay, so if you don't know what a positive closed current is, maybe it's not the right time to learn, but so again, so there is some very famous set of notes by Demailly where he's explaining this, how to interpret this, how to do complex algebraic geometry using basically currents, per stage functions. Okay, so let's come back to my favorite degrees and to this definition there. All box formula are yellow. Yes. Okay, so just to be sure, so I have X, F, X. So recall that I look at this diagram where gamma hat was the resolution of singularity of the graph. So the degree k of f, what I said, this is f star c1 of L, which k, sorry, d minus k. So what is this? This is a pullback and push forward. So still, this is a bit painful because I wave my hand with the action by push forward and pull back on H2k. But in fact, this is also the pullback so we can compute this intersection number, in fact, in gamma hat. So you're pulling back the first chain class of L to wedge k, and dot pulling back by pi 1 wedge d minus k. And then when you see this, so in fact, pulling back commutes with the intersection number, with intersection product. And so you get back exactly to the situation where you define intersection numbers of cycles. Okay? So here what we do, this degree k, which depends on the choice of L, of F, is computed inside gamma hat. You're pulling back your first chain class, so this guy is ample, right? So you're pulling back to gamma hat. You take k times the same pi 2 star of C1 of L, and then do the same for pi 1 star and compute intersection. So what I said, this is, it's not a real number, it's an integer number. But in fact more, because pi 2 hat of C1 of L, and the same for pi 1, or an F. How do you see this? Well, okay, you kept this with your favorite curve. You want to say it's F, so you've kept it with your favorite curve. And this is C1 of L dot the push forward of C, but now C1 of L is ample, so intersect any curve positively. So maybe this curve is inside the exceptional locus so that its image is 0, so you might be unlucky, but at least this is non-negative. Okay? So what I said is that this number is the integer number, then I'm cheating. I'm saying that this is positive. Okay. So what is the intuition? So maybe behind this, so I think, well, I don't think, I'm sure, that Serge is going to come back to this, but I'd like to make still some comments. So what this number control about F, and what I want to say that this control the cohomological class of gamma. So we already saw this in the case of when I estimated the number of periodic points for a rational map from P2 to itself. I said, well, the graph, the cohomological class of the graph is determined by the degree and the topological degree. Okay, so you have to understand that these numbers, so there are d plus 1 of them. K is in between 0 and d. So I'm not saying that this number determines the cohomological class, but it controls this cohomological class in some sense. In which sense? So yeah, again, I'm going to use some complex geometry. So look at the Keller form. Let's say whose class is the same as C1 of L. So how do you do that? You put positive matrix on your favorite ample-line bundle. And then what you can do, so this Keller form, this is a positive definite 1-1 form, closed. And so it defines a metric. And you can restrict this metric to the graph and compute. So since the graph is complex analytic, it's oriented, and so you can compute the volume of this graph with respect to this metric. And so the claim is that, in fact, the volume is controlled very precisely. So you can estimate it very clearly. It's by Vertinger. So this is integral over the graph pi 1 star omega plus pi 2 star omega to the power d. And so this is a linear combination. I'm not going to make the computation precisely, but this is a positive linear combinations of the degrees. Okay, so if you give me all these degrees, then in fact, I know how big this volume is. So I can control somehow how big is the class of gamma f inside the cohomology of x cross x. Yeah. I hope so. There's binomial coefficients or something, yeah. Okay, so now this is the time. Yeah. Are you ready? Okay, so now I have to prove the submultiplicativity of the dynamical degrees of the degrees. And so let me state the theorem and then draw some consequences. So okay, so our notation, so x, y, z, projective, smooth, varieties, all of them of dimension, the same dimension, d, and then you have ample line bundles, Lx, Ly, Lz, okay? And so the statement is like this. There exists a constant c, which depends only on the geometry, the geometrical data, so let's say on Lx, Ly, and Lz, which is positive, such that if you, for any rational dominant map from x to y and g from y to z, then if you compute the degree k, so I'm going to be more precise by what I mean by this, okay? So degree k of g composed with f is less or equal to constant times degree k of g times degree k of f. Okay, so this is exactly what we saw in the case of the projective space, where x, y, and z were the projective space of any dimension, and k is equal to 1, and Lx, Ly, and z is O of 1. Okay, so here I have to be a little bit careful, because what I did was to define the case degree respect to one polarization for a self-map. But you can do the same kind of definition here, so let me for instance, define degree k of f. What is this? So you have the same diagram as above, but you go from x to y, right? And so you take exactly the same thing, except that you pull back pi 2 star, and then you look at c1 of Ly to the power k, dot pi 1 star c1 of Lx to the power d minus k. And the same thing for g. So maybe I screw up and g, no, okay. Okay? Okay, so before I explain how to prove this, let me draw some consequences, simple some consequences of this. Okay, so we already saw these things in dimension 2, but we can take x equal to y equal to z, Lx equal to Ly equal to Lz equal to L, and then you take, okay, let me take capital F, okay? So you take a small f to be capital F to some iterate of capital F, let's say f to the n, and g f to the m. And so what you get is degree of capital F n plus m is submultiplicative. Well, sort of. You have to multiply by this number c. You have some error bounds, but sorry, you have some error, multiplicative error. But then it's uniform. This constant c does not depend on this rational map f and g, or on the iterates here, the integers n and m. And so you can look at c, you can multiply on both sides by c, and then you see that there is too many c in your c. You're far from the c. Well, okay, fine. So this is submultiplicative. Okay, and so this means that c degree k of fn to the power 1 over n converges. Okay. And its limit is this famous lambda k. Now c to the power 1 over n tends to 1, so you get what you want. Woo! We have the dynamical degrees. Great. So a priori, these dynamical degrees depend on the choice of the ample line bundle. So here I have to explain why it doesn't. And also I have to, so I said this at the very beginning, this dynamical degrees of birational invariant. And so all of this is a consequence of this theorem. Okay, so what is, let's say, a statement that contains both of things. So you have y and pi, which is, so you have a diagram like this. So let's say pi is birational. F and G are dominant, so all of dimension D. And then you have Lx, Ly, ample divisors. And so you can compute lambda k of F. Let me put comma Lx to emphasize the fact that I'm computing with respect to my choice of polarization on X. And the claim that this is Lk, Ly of G. Okay, so here I need this diagram to be commutative, which means that G here is equal to pi composed with F composed with pi minus 1. Okay, so how do you do this? Well, such an inequality, you get Gn is equal to pi minus 1 composed with Fn composed with pi. And you apply this lemma, well, this theorem, sorry, twice. And so you get the degree k of Gn bounded by constant time constant time constant, so new constant, C hat, time degree k pi minus 1, degree k pi, degree k Fn. You take the nth root of this, and then you can an upper bound. So this guy is less or equal to this one. And then you play the same game with f is equal to pi composed with g composed with pi minus 1, and you get the other bound, hence the equality. Okay, so the remark here is that I could have taken pi equal to identity, so x equal to y, and then I'm choosing two different line bundles. Okay? And again, so this works perfectly, and in this case, I'm concluding what? I'm concluding that the dynamical degree does not depend on the choice of the line bundles. So, in fact, it's a bit more precise, but if you change your line bundle, then the sequence of degrees are not, the numbers that you get are not going to be the same. They're different. But the rate of growth of this are comparable. So here I have a weaker statement that their dynamical degrees are the same. Okay? Okay, so, yeah. Great. So, let me keep this. So there's one more statement I want to make about these degrees, and then I'll explain the proof of this multiplicativity statement, at least in the case k equal to 1. Okay, so facts. So the dynamical degrees are log concave. So is log concave. So what does it mean? It means that, okay, so let me draw just the picture. So here you have the integers 0, 1, 2, blah, 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 till d. And then you look at the function log of lambda k. Okay, so the first one, so let me recall that lambda 0 is always equal to 1. Lambda d is a topological degree. So you start like this, and you get a sequence of points. Okay, and what I'm saying that this function is concave. So in other words, for all k in between 1 to d minus 1, lambda k to the square is at least lambda k minus 1 times lambda k plus 1. Okay, and I think I explained this in the case for, already explained this for surfaces. in the case of x is equal to p2. So what this statement say that lambda 1 to the square is at least lambda 0 times lambda 2. Lambda 0 is 1, lambda 2 is a topological degree. Okay? So this is this statement is classical. In fact, it's a direct consequence of the Hodge-Index theorem on surfaces. So let me give a very quick proof. So this is Hodge-Index theorem on surfaces. So what it says? It says that on surfaces, if you have what I want to say. So if you have two classes, alpha and beta, let's suppose they are F. So this implies that the intersection non-negative. And then if you look, so suppose that alpha and beta are not. Okay, so if the vector space generated by alpha and beta is two-dimensional, then the restriction of the intersection form has to have a negative eigenvalue. So this can be translated as saying that you have a Cauchy-Schwarz inequality, but in the wrong sense. So you have alpha beta square is greater or equal to alpha square beta square. Okay, so if you believe in this, then how do you go to a higher dimension? So you take d ample line bundles. L1 to LD. And then you look at S, where the surface. Well, you take a general section of L3 dot L4 blah 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 dot LD. General section. And then you can apply now the Hodge-Index theorem on surfaces for L1 and L2 restricted to S. So this says L1 restricted to S dot L2 restricted to S. The square is L1 square, L2 square. And so what does it mean? It means that you have the following thing, L1, L2, L3, blah, 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 LD to the square is greater or equal to the product where you replace 1 by 2 and vice versa. So L1 square dot L3 blah 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 LD, L2 square L3 blah 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 LD. Okay? And so if this is true for any ample line bundles, it's also true. Maybe I should not have erased this, too late. So it's also true for NEF classes by continuity. And so you apply this. So exactly what I raised here. So you in gamma hat, pi 1, pi 2, x, x. And so you let L1, which is pi 2 star of C1 of L, blah, 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 LK, pi 2 star of C1 of L. No. Okay, sorry. It's, okay. Sorry. If you really want to see that this implies what I claim, so you have to say that pi 2 star of C1 of L, this is L1, L3, blah, 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 L. You need K of them, so LK plus 1. And pi 1 star of C1 of L, this is L2, AK plus 2, LD. Okay, so what I said is that they are not necessarily ample, right? So here I said, okay, it's true if it's ample, fine. But then it's also true if the LIs are NEF. It's okay, by continuity. So these guys are NEF, so you apply this inequality, and what you get is precisely what you want. So you get the degree K of F to the square greater or equal to the degree K minus 1 of F times degree K plus 1 of F. Okay? Okay. And since I have to make some advertisement for my own work, so we prove with backdown in full generality that if lambda1 is greater than lambda2, so remember, so this is completely general. This inequality is completely general, and what we said is that if there is a strict inequality, then in fact you can control the degrees, index 1, and so it's C lambda 1 plus this plus mu to the n for some mu strictly less than lambda 1. Anyway, so yeah, okay. So now in the remaining time, there are a lot of things, yeah, 20 minutes. So in the remaining time, I'm going to focus on this huge theorem. And then if I have like 5-10 minutes left, then I come back and make some more comments on how you compute these dynamical degrees, let's say in the regular case and so on. But I doubt I will have much time. Okay, so I'm going to explain this result in the case. Okay, maybe first, who proved this first? So this is a theorem which is due to, sorry, yeah. What? No, it's a theorem, is right, please. My theorem. Yeah, in dimension 2, you know that, okay, so in dimension 2 for birational map, lambda 2 is equal to 1, and so what you're saying is that lambda 1 is equal to 1. And in that case, you know that the degree grows polynomially, either it's bounded or linear or quadratic. And so you don't have like a purely exponential thing, okay? Yeah, well, okay, sure. In the case lambda 1 is equal to 1, I'm not sure exactly what this means, but yeah. Yeah, you can, yeah. For instance, yeah. So what is expected is that if you have equality, then in fact the degree of fn, well, expected, I'm not sure. But question, is it true that in fact the leading term is like a polynomial in n times lambda 1 to the n? So this we don't know, except for birational surface map, or monomial maps, or regular endomorphism, or yeah. Is it okay? Okay, so proof of this. So what I was saying is that so this proof was a proof was first given by Dean and Simodi. And their proof really used currents, so it's really analytical. So it's used positive closed currents, regularization of positive closed currents, and so on. So what is a good point about this proof is that it's a bit more general. It's not only, it works on not only for projective varieties, but also for Kähler compact manifolds. Okay. Sometimes it can be, I mean, you have examples on of a rational map on, well, rational, I don't know, meromorphic map on the Kähler varieties. So, and then it was, so I don't remember the dates, I didn't, yeah, 2010 star, then Thuyen Truong and Backdown proposed a new proof, purely algebraic proof, that works over any field. So here you can argue that if you're over a field of characteristic 0, of course you can embed this field into C and then use the analytic argument of the Insiboni and then you're done. But over a field of positive characteristics, it's a bit unclear, okay? But at least the proof here were completely algebraic. And so I'm going to explain the proof by Dong. Okay, so the key word is so-called Hughes inequality. And so I'm going to write that down and then explain why it can be used to prove these things. Then, if I have time, so I'm going to explain this for k is equal to 1, but then the proof works for any k. So here the proof is going to be equal to 1. So this is these two inequalities are very nice because it's very simple, very general. But then you have to be a bit careful about the statement because it mixes these two definition of these two notions of positivity. You have the nefness and the effectiveness. So the statement is as follows. Okay, so you take A and B ample line bundles. So again, on X. So yeah, X, smooth, projective, blah. Projective is important. The fact it's smooth is not important. The fact it's ample, you can generalize, I will see. And the claim is like this. Let me write it down, and then I explain. So it's A is less or equal to A times B d minus 1 over B to the d times B. Boom. Okay, fine. So what does it mean? So it means you take any two ample line bundles. Then if you look at B times this number, let me call this number T. This is a rational number, right? Because it's D, it's a dimension of X. And these are integer, positive integer numbers because A and B are ample, so they are positive. In particular, this B to the D is positive, so you can divide. So this is a rational number which is positive. So what you claim here, what I claim is that T times B minus A is pseudo-effective. And in fact, here, if you take any T which is strictly larger, is actually effective. So let me say, so for this is effective for any T prime strictly larger than T. So this is a claim. So you have to be careful because here you're playing with ample line bundles. And the conclusion is not that the difference is ample. The difference is effective. Okay? So this is a bit tricky and can be a source of some mistakes. Okay, so let me... so this is a margin of the set of notes by Fermat. Okay, so let me draw the proof of this fact in this even tinier margin. Yeah, the proof is given in the beautiful book by Lazarsfeld, volume 1, page 117. I don't know. Yeah, well, what I want to say. Yeah, the proof is something like this. So you reduce, just to tell you that this is basic algebraic geometry. So you suppose that B to the D, what you prove is you suppose that you have two ample divisors such that this inequality is satisfied. Okay, and what you show is that if you compute the set of sections of NB, okay, so I always use multiplicative things, so let me turn to linear now. So NB minus NA. We're going to show that this growth, like n to the d times some constant, plus big O of nd minus 1, where the constant c is positive. So this is, I'm looking at the linear system, nb minus na, and when I'm saying that there are a lot of sections, at least if you multiply by some huge divisible n. Okay, so yeah, if this is true, then in particular it is plain, so since I have, it's sufficient to have just one section to claim that nb minus na is effective. Okay, so this implies that B is greater or equal to A. So how from this statement you get this? Well, play around with rational numbers. So if you play around with this, you apply this lemma to not to B, but to T times B with T rational. So you might have to multiply by the suitable denominator and so on. And this statement implies this one. And how you get this statement there? It's a restriction argument plus asymptotic Riemann roch. So it's really elementary, but extremely powerful. Okay, so now I have to explain how from this you get this crazy statement, at least for k is equal to 1. Okay, so first thing first. So we need to play a little bit with classes that not necessarily ample, and so consequence of a pseudo inequality is that if alpha and beta are Neff classes, they are limits of ample classes. And so you see that since the pseudo-effective cone is closed, you can take the limit and get exactly the same inequality. So alpha is less or equal to d times alpha beta d minus 1 times beta divided by, oops. Okay, I have to be careful because before B was ample, and so its top intersection numbers is always positive. Here, it's not necessarily the case. And so I have to add this important assumption that the top intersection number of beta is positive. And in this case, I get this inequality. Okay? Okay, and so now I cannot avoid writing down this 9 minutes. Yeah, so 8 minutes to write down the diagram, and 1 to give you the proof. So I want to prove this using this. Okay, let's go. So we have x to y to z. So my notation are like this. So okay, so let me take gamma 1. It's a resolution of singularities of the graph. Of f. And then you have gamma 2, the resolution of singularities of the graph of G. And let's say this is P1, P2, Q1, Q2. Okay, fine. But I also need the resolution of the graphs of the composition, F composed with G. And so what I'm going to take is gamma 3, like this. And this is going to be pi 1, and here pi 2. Wow. Okay, so I have 3 ample line bundle, Lx, Ly, Lz, and I need to compute intersection numbers all over the place. So just to simplify notation, I'm going to use only one letter, L, for Lx, Ly, and Lz, right? I mean, at this point, it's... And also, because I want to simplify, I'm just going to change notation and to write omega as C1 of L. So this is this class in Nx of Z, which lives here. And so if I want to compute the degree of G composed with F, I'm going to start with these things and trying to pull it back. So first by G, then by F, or by F composed with G, like this, okay? Okay, so let's go. So I need to understand, so what is the connection between G composed with F star omega and G star F star omega. Okay, so let's start. So omega is here. And so you have to pull it back, to go to the left, from the right to the left in this diagram. So let me start by pulling back by Q2. Okay? So I'm pulling it back by Q2. I'm here. And then to pull it back by G, you have to go down to by Q1. Before I'm doing this, I'm not going to explain, but I'm going to apply SU directly. To what? So I'm going to apply SU to the pullback. So these guys maybe I should so blue. So this guy is birational, this guy is birational, this guy is birational. So if you want gamma 2 is a birational model of Y. Oops, sorry. Okay. So I'm going to apply Su to the pullback of omega by Q2 and the pullback of, yeah. Ooh la la. Okay, so in my wonderful notation, there are the three classes. There is maybe it was not a good idea. Okay, let me not do this. It's already so omega z. This is C1 of LZ. Omega y. This is C1 of Ly. Omega x. This is C1 of Lx. Okay, and I want to compare this. So omega z is here. Omega y is here. Omega x is here. And I'm going to apply Su to pullback by Q2 of omega z versus Q1 pullback of omega y. So I know there are these two things are nef, and I want this to, so if I want to apply this Su inequality, I need to check. So beta is going to be a Q1 star of omega y, so you need to check this. And then the point, so this guy is nef, where in gamma 2, and Q1 star omega y to the power d is in fact omega to the power d. So it's positive. Because intersection is, and pullback, the pullback maps is preserve intersection pullback by birational maps. Okay. So now what you get is Q2 star omega z is less or equal to d times. So below we have Q1 star omega y to the d, and upstairs you have Q2 star omega z dot Q1 star omega y d minus 1. Whoops. And this. Okay, fine. So equal. So it's d divided by some constant. And here what you recognize is that you're pulling back this form here, and you're pulling back d minus 1 times this form. So this is exactly my definition of the degree of G with respect to all this polarization. Ah, great. Okay, fine. So I'm not sure where I am now, but now I'm going to pull everything by pi 2. So there is one thing that I didn't explain, is that in terms of okay, fine. So the pullback, it's probably not the optimal proof, but whatever. So here it's the difference is pseudo-effective, and the pseudo-effective divisor, they're stable by pulling back. So I can pull this back by pi 2 to gamma 3. So this is less d over omega y to the d degree of G, pi 2 star, Q1 star, omega y. And now what you do is that you cup this with an F class, which is the pullback by pi 1, by p1 and pi 1 of omega x to the right power, d minus 1. So you take this curve class, omega x to d minus 1, and you pull it back there, and you cup everyone. So here you're intersecting, here omega x is ample, so when you're pulling back is nef, and you're intersecting d minus 1 of these kind of things. And so if you're intersecting this with an effective divisor, this stays effective. So when you cup this, you get two numbers, and the left-hand side is going to be still less or equal than the right-hand side. So what you get on the left-hand side, by definition, you're pulling back this guy, cupping with this one. So this is the degree of the composition. So G composed with F. And what you get on the right-hand side, you get D over omega y to the D degree of G. And then I'm completely exhausted, and so it has to be degree of F. I hope. Okay, so do you see why it's a degree of f? I'm not sure. Because what? Pi 2. Oh. Yeah, because so when you kept this, so you have, we are looking at the pullback by Q1 and pi 2, but this is the same. So this diagram is commutative, so Q pullback here is also the pullback by P2 and pi 1, okay? And so here you're capping with pi 1 star of things, so it's the same as computing everything in gamma 1, which is the degree of f. Okay, fine. I'm sure you can redo this computation. Oh, it's time. So, so exercise, do the same proof for general K. So let me take just 1 minute, okay? So and for general K, in fact, what you need is to have this kind of inequalities where you replace alpha by alpha to the k and beta to the k. So here, the statement is that there exists some constant which is universal, depends only on the dimension d, such that for any alpha and beta nef, such that the volume is positive, so beta to d is positive, you have something like this. Proof of this is, so it's given by, in the paper by Pak-Dong, and it's, yeah, let's say it's a direct consequence of Sew's inequality, but you have to apply this several times in a clever way, okay? And then there exists some kind of analytic proof with a better constant. And once you have this, then you can play exactly the same game. So I'm cheating at some point here, but you get, from playing exactly the same game with the same diagram, you get the submultiplicativity there, okay? And then I think I need to stop, so thank you.
Is there any question?
So about your theorem with Bach, if you assume not that lambda 1 squared is bigger than lambda 2, but another, like let's say, another strict inequality like with lambda k and lambda k plus 1 and k minus 1, do you think you can get the same growth of degree for the k one?
Who knows?
Maybe you?
Yeah, well, you know, I thought for many years that all dynamical degrees were algebraic integers, so I don't say anything. The proof is, you know the proof, right? Because you read all my papers. So you're looking at the action on the suitable Banach space, and you're proving a spectral property, a spectral gap property, and it comes from this strict inequality. So if you said just this way, there is a priori no reason why you cannot do anything in higher codimension. But the key is that in codimension 1, we have a very, very good understanding of the properties, and even at the complex level, this is much, much, much harder in the higher codimension.
Okay. So
I don't know.
Follow-up question, what about periodic points?
Yeah, okay. So can we cancel the last lecture of the next speaker? So yeah. So this is this theorem, this deep theorem by Nguyen and Dean. And what they say is that for any rational map of dominant rational map on X, let's say even compact Kähler, meromorphic blah, then the number of isolated periodic points of period L, you take the lim sup 1 over L. This is less or equal to the max of the all lambda k. So if you're over the projective space, the same argument that I gave is working perfectly, okay? For homogeneous space, the same. But then if you're over a general projective variety, then it's much harder. And so they use analytic arguments. We need some rest.